What's up everyone, this is Danka, co-founder of AIMP Poland, JS Poland, AI Poland and Angular Master.dev. Welcome back to the AI Master Podcast. Today we've got a special guest from Hungary, mathematician, educator and author of Mathematics of Machine Learning. He is on a mission to make complex concepts simple. Ladies and gentlemen, Tivadar, Danka. Hi Tivadar, how are you?
Hi, I'm awesome, thanks. How are you?
Perfect, thank you so much. For those who don't know you yet, please tell us about yourself and what you do.
So by training, I'm a mathematician. I finished my PhD about 10 years ago. Saying that makes me feel a little bit old. Never mind. After my PhD, I moved towards machine learning research. I started in a computational biology group. I was mostly doing computer vision on microscopy images. And basically that was my introduction to machine learning, deep learning. It was around 2016. By the time deep learning became accessible to everyone, the time when Keras came out, TensorFlow was already established. PyTorch was beginning to rise. So it was a golden era, and that's when I got introduced to convolutional neural networks. And ever since then, I'm basically doing research and education in machine learning.
Your book, Mathematics of Machine Learning, is already making waves. What motivated you to write it? And who is the book really for?
So my motivation was basically that whenever I read a machine learning book, the notation was confusing to me. In most of the books, they conflated certain concepts. Like, for instance, most books, or not most, but some books don't distinguish between distributions and density functions in probability theory. So I decided to basically write a new book from scratch. And it started by posting these short explanations on Twitter, mostly, which is an unusual platform for educational content, I know, but back in the day, around 2020, it was like a good platform for education, and that's where the book grew out from. The audience is basically everyone who is struggling with mathematics, and not necessarily only for machine learning engineers. Actually, the topics I cover 3 topics: linear algebra, calculus, and probability theory. I think these are the fundamentals of mathematics for engineers, computer scientists. Basically, my aim was to bring these topics closer to them, because I know that if you are fluent in mathematics, then you can basically do anything, learn any framework, read any research paper, advance much quickly in your job, solve problems quicker. So my goal is to help them bridge the gap between theory and practice, because mostly mathematics is taught by mathematicians, which is not necessarily a good thing, because they mostly focus on topics that's important for mathematicians but not necessarily for computer scientists. And I wanted to change that. I wanted to write a book that is focused on applications first, mathematics second. So I don't want to overwhelm the reader by unnecessary technical concepts or complicated proofs. I just aim for the minimum amount of material which is maximally useful for the reader.
Has writing the book changed how you see your own work or career in any way?
Yeah, basically I realized that I love education much more than I thought. Like, when I was a PhD student, I don't know, more than 10 years ago, I was focusing on research. I was not focusing on education. And ever since I started to basically teach people mathematics, I realized that this is a very enjoyable thing for me to do. Like, I enjoy teaching, which I didn't know before. And basically writing the book is the culmination of my love for teaching.
What was the biggest challenge you faced while writing the book?
So when I started to write the book, I basically quit my job, and I did this full time as an independent writer, researcher, whatnot. And the most difficult thing for me was to make a living on the early access of the book. Right? So I saw the early access copies for my book, and the deal was that you pay for it now and you get each chapter as I write them. And during the writing the book, I had to basically focus a lot on marketing stuff, like promoting the book on Twitter, creating content on social media, writing a newsletter and whatnot. And this was the most difficult thing for me to do, because no matter how, basically the topics I used in the book are the same that I used in social media to promote the book, but the formats are really different. And switching from one format to the next is like very tiring. It's a lot of editing, drawing figures and whatnot, and I had to put a lot of time into basically building a social media profile, which was challenging because that took away time from writing the book. That's why the book took 4.5 years to write. That's a lot of time, yes. But I think the results are quite good. I'm satisfied. Of course, you can never be 100% satisfied with your work. But after the editing process was finished, I was satisfied with the book, how it looks, how it flows.
Many developers fear the math behind ML. What would you say to someone who feels not smart enough to tackle linear algebra or calculus?
The number one thing I would say is that I almost failed my math class in elementary school. Like, I was not a good student, and I was struggling with mathematics. And once I had supportive teachers, it all changed. My teachers, basically when I moved from elementary school to high school, I got a new band of teachers, and they were much more helpful to me. They explained material better. They were more patient. And that was the time when I basically started to understand and enjoy mathematics. And I think this is true for most people, because not understanding something can make you feel stupid. And if you feel stupid, then you don't enjoy that particular thing that makes you feel stupid. So you probably skip it or don't do it at all. And if you have like a supportive environment, it can change your perspective on the topic.
How do you decide which mathematical concepts are essential and which can be skipped when teaching beginners?
When I wrote the book, instead of starting from the math, I started from machine learning. I looked at where do I want to arrive, and I backtracked towards the fundamentals of mathematics. And this is how I basically assembled the chapter structure, the theorems, definitions, results, concepts in the book. And this is like I think it's a good advice for anyone who is trying to learn not only mathematics but anything, is to focus on the problem you want to solve. This can be an engineering problem, like a research problem, whatever, and then you backtrack from that, because that is the most effective way to learn. Like if you discover a concept by our problem, then you will deeply understand it, and it will stick with you longer than if you read about it in a textbook. Because if you just read about it, you will forget it within a couple of weeks or months. After you took the exam, you forget most of the material. But if you use the concepts daily, they will stick to you.
You said you want to democratize machine learning. What does that mean in practice, and how do you think education needs to evolve to support that?
The democratization is already happening, because most of the high-end machine learning courses are available online. For instance, MIT open source their course. You can find most of them on YouTube. Stanford records their courses and puts them on YouTube. So this is like a great democratization process that has already been going on. But what I usually mean in aspects of my work is that I want to bring theory closer by basically providing these visual and intuitive explanations, instead of focusing on like complicated formulas, proofs, whatnot. For me, it's like mostly intersection of mathematics and storytelling. So this is what I aim to do.
What's one mathematical idea you wish every software developer truly understood?
That's a great question. One mathematical idea every software developer should understand. I think there are some. I won't mention a concrete concept, because I think the most important thing you can learn from mathematics is how to think, how to solve problems. One of the most important ideas, I think, is that if you change perspectives, you can solve problems more easily. For instance, different representations are available for the same object, right? This is true in mathematics and computer science as well. So for instance, in mathematics, we can talk about graphs, but graphs can be translated to matrices. And most of the time, if you cannot solve like a graph theoretic problem, you might want to take a different perspective and convert your graph to a matrix and see if you can solve the problem by linear algebra. This is a very, very ubiquitous idea in mathematics. And this is true for computer science as well, because sometimes you have an object which has multiple different implementations. For instance, speaking about graphs, we can represent graphs as a list of nodes and edges, but you can also represent a graph as a matrix in a computer, and that can help you a lot in certain applications. I think this is one of the most important ideas to understand for any computer scientist or engineer.
Can you explain why understanding concepts like eigenvalues, gradients, or probability distributions is so crucial for machine learning practitioners?
So let's start with probability distributions, right? Because I think that's one of the most important concepts to understand. Predictive models are usually probabilistic, even if they not appear so on the first glance. So whenever you make predictions, you always have underlying uncertainties, and you have to make decisions under uncertainty. And understanding how to work with uncertainty and reason under these circumstances is very important. If you want to move, beyond like the mechanistical understanding and implementation of machine learning, if you really want to know what a model is doing, you have to learn probability theory. In turn, like distribution is a concept in probability theory, which is a very nice way of summarizing information from a random phenomenon. Eigenvalues are important because they are essential in the theory of matrices, linear algebra. For instance, principal component analysis has eigenvalues beneath the surface. But I think the most important part of math for any computer scientist is learning the language of computer science and learning how to think. I think that's the most important. And eigenvalues, distributions, probability densities, whatnot, they are tools of thinking, mental models, so to say. And by spending time and understanding them deeply, you will become a better problem solver. Your thinking will be better.
Hi, my name is Derek Kalbarczyk, and you are listening to the AI Master Podcast by AI Poland, a space where we deep dive into how artificial intelligence is changing the way we think, work, and live. Thanks for tuning in. If you are enjoying this episode, take the moment to subscribe the channel and ring the bell so you never miss a new conversation. Are there any real-world ML use cases where misunderstanding the math can lead to major issues?
I have spent quite a while debugging, for instance, PyTorch code because of tensor mismatches. Another example, which is one of my go-to examples when I'm asked this question, is the choice of the loss function, which is a mathematical concept. And I have seen engineers use mean squared error to train classifiers, which is conceptually wrong, because the mean squared error is not designed to deal with classification problems. It's designed to deal with regression problems. Although it works. You can do that, but you shouldn't. This is one of the most important ways, I think. Even in my practice, when I was in computer vision and biology, sometimes choosing the right loss function can make or break a model. And basically, I was able to successfully solve problems just by that skill.
What are some of the most common misconceptions or mistakes people make when trying to understand the math behind the magic?
Thinking that probability densities and probability distributions are the same, for instance, this is a common mistake. But I think what people have to realize is mathematics is a language, and most people don't treat math as a language. They treat it like something else, and they get hung up on formalism instead of the big picture, because most textbooks are written by mathematicians and they present mathematics in a really formal way. And the big picture, so to say, are hidden behind the lines, which mathematicians can read, but it's difficult. It takes something called mathematical maturity, which is what you don't have when you start out in mathematics. And this is why the learning curve is so steep. So what I would recommend for anyone who is trying to learn mathematics or any theoretical problem is to basically try to look at what assumptions are there in a result, take away assumptions, add assumptions, look at special cases, for instance, and don't try to take everything that seriously. Don't be afraid to break things. This is true in computer science as well, right? So whenever I'm implementing some kind of functionality or framework, whatever, one of my first thing to do is try to break the code I wrote, because by that I will understand it much better and I will be able to make it better by fixing the potential errors. And this is true in math as well. Whenever you read like a mathematical result, always question the assumptions, try to bring the results, so to say.
One of the things people love about your content is how intuitive it is. How do you approach explaining complex mathematical ideas in simple ways?
I don't really have a specific formula for that. I'm mostly a very disorganized and creative person. I don't have a template to my work. I just ideas pop up into my head sometimes when I'm taking a shower and when I'm dishwashing and whatever. And I always try to visualize. I just said that I don't have a recipe, and I don't have a concrete recipe, but visualization is almost always part of my work, right? So if you take a look at any of my posts or even the book, I have hundreds of images, lots and lots of images in the book as well. One of the first thing I do is try to visualize the problem. Most of them, it works quite well. Also, I try to put the problem into perspective for computer scientists and engineers. Like if you have, for instance, like a formula, like, I don't know, entropy, it's not that interesting in itself. It's a mathematical formula. It's quite dry. But for computer scientists, information theory is pretty interesting, right? And if you start from the applications and the interesting stuff and then work your way back to the formula, it becomes more interesting. So it's kind of a storytelling technique. Visualization and storytelling. I think this is the two of my most liked aspects of my work.
Do you see math as a creative process, especially in context of building models and algorithms?
Yeah, sure. Like as I said, I'm a disorganized and chaotic person, so I see everything as a creative process, and I'm really, really resistant towards any kind of rules. I'm not a person who works well within strict set of rules, and this can be applied to workplaces, right? So I had a couple of jobs in my life, and let me tell you, they did not go well. So most often I'm fired after a couple of months. So there are only a few people who can tolerate this. But in content creation, this can actually work quite well. And in education research, my blatant disregard for rules and authority.
In the book, you also include Python-based examples. How do you balance that theory with practical coding skills?
I think one of the most important ways to learn any mathematical concept is to implement it in practice. For instance, in the book, linear algebra part, we implement all kinds of matrix factorization techniques. And whenever you try to implement something from scratch, it really gets ingrained in your brain. I think building things from scratch is the best way to learn, hands down. This is why I find it very important to always put the theory into code. And this is why basically the chapter structure in the book alternates. So one chapter is about theory, next chapter is about practice. First, I talk about vectors and vector spaces. Then we look at how vectors are implemented in Python, and we learn the NumPy library. Then it's about matrices, how matrices are formed. Matrices, as a theoretical mathematical objects, they are linear transformations, but on the computer, they are basically tables of numbers, and how can we work with them? This is how the book is basically built. And I think it's essential. Whenever you try to basically learn technical subjects, trying to implement it from scratch is number one thing to do, at least for me. Right now, I'm working on a educational library where I implement computational graphs from scratch. So right now I'm working on adding the convolutional layer, so to say. And this is my way of understanding deep learning very well, very deeply.
How did your background in pure mathematics shape the way you understand and teach machine learning?
So mostly I'm approaching things from a theoretical perspective. Whenever I am familiarizing with myself with a subject, it's the other way around when I teach. But when I try to understand something, I always basically my mathematical education always kicks in, and I try to basically identify the mathematical patterns and abstractions behind every concept or algorithm or whatever. Usually when I teach, it's the opposite.
What role do you think AI tools like ChatGPT can play in helping people learn or even teach mathematical concepts?
I think they are great for learning, mostly because they are excellent in finding new information, finding and summarizing information online for you. One of the number one learning workflows I have is I use Google Gemini to create like a deep research report about any subject. And then I use, again, Google's Notebook LM to convert it to a podcast and listen it while I'm washing the dishes or doing something mundane, like, I don't know, biking or whatever. And I think they are excellent in that aspect. However, on the other hand, they are not good in actually solving problems that are unsolved. If someone had the same problem that you have and they ask the Stack Overflow question about it and someone solved it for them on Stack Overflow, then the large language model will be able to pick that up for you because they were trained on that data. But for really, really novel problems, research problems that no one knows how to do, LLMs won't be able to work to help you. But for teaching things, I think they are excellent. Not necessarily using LLM as a teacher, but mostly using LLM as a supercharged Google search. Back in the day before Google happened, basically we had to have encyclopedias and have to find information on our own, and Google changed that. And now we don't even have to Google because now large language models synthesize and compact all that information to us. So I think it's great. If you learn how to ask really good questions, your learning process will be accelerated very much.
If someone wanted to really master the math of ML, what would you recommend as their learning path besides your book, of course?
Always start from a problem, because at the end we want to build things and solve problems. If you already have like an established career or established area of research or something, then you should always approach from the problem perspective. If you are a student and you don't already have like a portfolio of projects, then learning from a textbook is great. But I think it's always best to build something. And whenever you stumble upon a mathematical concept that you don't understand, you try to look it up, and from there you backtrack it until the point where you can understand things. Until you meet some concepts that you already know, and then you build on that. I hope this makes sense.
As ML tools get easier to use, do you think it's still important to understand the math behind them?
I think it will be less important for users, but more important for people who are building the tools themselves. For instance, think about think about C versus Python, right? So back in the day, before Python, before object-oriented programming, everyone basically programmed the lower level languages like C or assembly or whatnot. And as the ecosystem and the programming languages grew, they moved towards Java, Python, whatever. And those people who work on the top of the abstraction layers, they don't have to understand C. But the people who are building Python, they have to understand C very well. For instance, NumPy is built on C arrays. They call C functions. So for the people who build the tools that make things easy for the users, they have to understand the low level stuff really well. And this is true for mathematics as well. So if you are a machine learning engineer, and you are building that, if you're pushing the state of the art, then you have to know mathematics for sure. But if you are basically building consumer products from already built Lego blocks, then mathematics is not that important for you. Although I'm quite biased as a mathematician, I think if you learn math, you will learn how to think, and this is important no matter where you are in your journey. So basically, my answer to your question is both, right? So it becomes less important for the user, but more important for the engineer and the builder.
How do you personally keep up with both the fast pace of AI and deep theoretical research?
I don't, which is probably not the answer you expect, but I was just unable to while I wrote the book. And right now, one of my goal is to pick up the pace, so to say, to kind of get back on track with the research and move towards more in a research position. Usually, back when I was a researcher, one of my morning tasks was to browse the new papers on arXiv or on social media. If you follow the right people on social media, that can help a lot, because there are some people who put out high quality content in these aspects, that they publish the best and most important papers. Sebastian Raschka is an example. I hope I'm pronouncing his name right. Like he wrote the Python machine learning book, and he also has a newsletter. And right now he is focused on LLM engineering, and that's an excellent learning resource. So once in a while, in a month or so, he writes these summary articles about the latest developments in the field. And I think for anyone who works as a large language model engineer, this is golden, right? And no matter what is your field, you can find the people who do that. And I think that's quite important for you, because basically there is a new paper every second, hundreds and hundreds of new papers every day, and it's impossible to keep track. So follow the right people, and maybe even build like your own AI news aggregator machine, which, I don't know, scrapes the latest tools and research papers for you, and then summarizes them in a few sentences.
What's next for you? Any plans for follow-up book, a course, or maybe even a visual edition of mathematics, of machine learning?
I always have more plans than I can execute. So yeah, I'm working on a sequel. Originally, this Mathematics of Machine Learning book contained the part where I implement neural networks and convolutional networks from scratch. But as the content grew, I realized that I have to split the book into two. So number one half of the book became Mathematics of Machine Learning, which just released by Pact Publishing. It's linear algebra, calculus, and probability theory. But now that we have all the mathematics under our belt, it's time to focus on machine learning and implementing machine learning algorithms from scratch. And this will be the sequel, which is already halfway done. But after 1,000 pages of content, I decided to split the book in half. So that's my number one project right now, finishing the sequel. Besides that, it would be nice if I could get back on track with research and with open source frameworks. Before the book, before anything, I wrote a Python machine learning framework for active learning. It's called Modal. That became quite successful. It was, I think I wrote it in the Christmas break of 2017, and I really enjoyed that. And I think what I want to do after the sequel is finished is pick up a niche topic in machine learning and create the best open source framework for that. Right now, I have anomaly detection in my sights, which is a topic that was always interesting to me. I don't want to learn in large language models, which is surprising because everybody wants to work in large language models. But usually I'm attracted to more niche topics, like, for instance, active learning. Anomaly detection could be thought of as a niche topic compared to large language modeling. Sorry, large language models, not large language modeling. That doesn't make sense. So that's these are my plans. But I always have project ideas, and I just don't have enough time to execute.
My last question is, what's your favorite way to unwind after a busy day of writing a book or coding?
I cannot really unwind, to be honest. Like, I always have something on my mind. Most of the time I do workouts, listen to music, or maybe even cook a nice meal, but that's it. But even when I'm unwinding, I'm thinking about next thing to do. The only way I can completely unwind is to play some mindless video game. But this is something that I actually try to minimize, because that takes away my creativity. So I'm not a big person for unwinding. Like, my mind is always racing. Even when I'm doing, like, basically, I'm resting. I'm spending my brain power to come up with the next idea, next implementation, whatever.
Tivadar, thanks so much for joining me today. It was a real pleasure having you on the podcast.
Thank you. It was a pleasure for me to be here as well.